We're back. Okay, so we're going to look at second order circuits now. And it's really important that you give a good grounding in first order because second order circuits are way harder than twice as hard as first order. And the reason is because in a first order circuit, there's only one solution. It's either that integral if you have a function of time for the voltage source or the current source, or if those are constant, then it's that simple equation that we ended with in the last segment, I think. So in second order circuits, I just want to, before I actually do this problem, I want to outline basically your process. Can you get me here? Sorry. So for second order circuits, there's a process that you're going to have to go through. Now, if your circuit is one of the standard circuits, and by standard circuit, there's like a standard RLC circuit where you basically have a resistor, inductor, and capacitor in series with each other, or you might have them in parallel, okay, with a voltage source. So if you have one of these standard circuits, RLC, then you don't necessarily have to go through the process that I'm showing you. And you can do it in a really a much easier way. But I've decided to make my students learn the hard, more general second order circuit so that you can solve any second order circuit you come across, not just if they happen to be one of the standard RLC circuits. Okay, so in that more general case, the first thing you have to do is find the differential equation. And it's going to be a second order differential equation. And so if it's a second order differential equation, the most general form looks something like this. Right? I mean, here it is. That's the most general form of a second order differential equation. You've got some constant times the second derivative of your variable with respect to time, plus another constant times the first derivative of your variable with respect to time, plus the third constant times your variable equals some forcing function. So here is a second order differential equation. The solution, of course, is going to be some function of time. Now, depending on the circuit, of course, we'll give these values for A0, A1, and A2. And so they're going to be some kind of combination of the resistor, the values of the inductors or the capacitors or whatever it is you have in the circuit. That's going to determine the values of A0, A1, and A2. X, well, X is whatever you're interested in. It could be a voltage across a capacitor, it might be a current through an inductor, it might be a current through some other place in the circuit, whatever. X is your variable, though. It's either going to be a voltage or current that you're looking for, and the solution to this equation is a function of time. Okay, so once you find this differential equation, of course, you have to solve it, which, of course, you're going to take a whole course in differential equations. But again, the ideas that you need to apply to your circuits problems is that any solution, any complete solution, where you show your variable as a function of time, is going to have two parts, right? It's going to have the forced part of the solution, and then you're going to have the transient part of the solution, or the natural part. Okay, so I'm going to use the subscripts F and N, so the forced part and the natural part. It's this natural part that dies out as t approaches, as time goes on. So oftentimes, really, you're not that concerned about the natural part because it'll die out like a lot of times, like in microseconds. So it's not going to really matter that much, but we do want to be able to know what it is. In a lot of cases. In a lot of cases, we don't care what it is, and we only want to know what the long-term solution is, the forced part. But here, in this chapter, I want you to be able to get both parts, the natural and the forced part. And then I also want to remind you that I told you earlier that in these natural parts of the solution to the differential equation, you're going to have the same number of arbitrary constants as you have order of the solution. or order of the differential equation. So we are going to expect that that part of the solution has two arbitrary constants. And those constants will be determined, you can calculate them from knowing what the initial conditions are. So to solve the differential equation, first, well, I don't know, it doesn't matter whether you do first or second, but you're going to have to figure out what the forced part is, you're going to have to figure out what the natural part is, you put them together, and then you solve for the arbitrary constants using the boundary conditions, or the initial conditions, if that's what they are. So, this is the outline of how you approach these problems. So we're going to do this problem here, and I'm going to actually find that second order differential equation that defines this particular circuit right here, which we see is a second order circuit, because look, I've got 1, 2 energy storage elements. All right, so there's different ways to find the second order differential equation that defines the circuit. I like to do it, okay, and there's something called the state variable method. So that's where you have to define your state variables. So you're going to need 2 of them since this is a second order equation. And let me just give you some advice. Go ahead and just define your state variables. If you have a capacitor, take the voltage across the capacitor as one of your state variables. If you have an inductor, take the current through it as your other ones. So if you had 2 capacitors, then my 2 state variables would be 2 voltages, and so I might have to label them V1 and V2. Since I have 1 capacitor and 1 inductor, then I'll just call this V. I don't need a subscript because it's the only V I'm interested in, and I'll call the current through the inductor, I'll call that I. I'm actually being asked to find the voltage across the capacitor. So keeping that in mind, that certainly makes this a good choice for one of my state variables. Okay, so once you've defined your state variables, what you have to do is come up with an equation for each state variable. And basically what you're going to be doing then, you'll have one equation for each state variable. It's basically the idea of, since I've only got 2 state variables, I'll have 2 equations and 2 unknowns. I can reduce that to 1 equation and 1 unknown, which is ultimately what I want to do because I just want to have my unknown V. That's the only variable I'm really interested in right now because that's what I'm being asked to find. Okay, so I actually like to just go ahead and use like mesh current analysis or node voltage analysis to do this. So I'm going to go ahead and oh, I just realized something. Okay, I'm going to go ahead and label a reference node right here, and then here are some nodes. Okay, I'm realizing that I have a switch in this problem, and I'm really only interested in the values at t greater than 0. But the reason I need to look at the circuit at t less than 0 is so that I can find some initial conditions, so that I can use those later to evaluate those arbitrary constants in my natural part of the solution to the differential equation. So I don't know if it's a distraction for me to do that right now or not. I think I'm going to hold off on it for a couple of minutes and instead go ahead and show the switch in the position after t equals 0. So this is the circuit after t equals 0. This is just kind of hanging there. It's not really doing anything because it's not connected. So this is the circuit. I'm going to have to go back to what the switch was to find. We're going to need I of 0 minus and V of 0 minus. We're going to have to find those values because those will be our initial conditions to evaluate the arbitrary constants. And the reason we specifically want the current through the inductor and the voltage across the capacitor is because we know that those do not change instantaneously. So if we know their values right before t equals 0, we know their value at right after t equals 0. So we're going to need those. I'm going to get those later. But for now, let me just show the circuit at t greater than 0 because I'm trying to find the differential equation for that circuit. after t equals 0. So, you know, I'm going to erase this because this is even distracting. It's like that's not really doing anything. So here's the circuit at t greater than 0. Okay.